Hey, it's Mr. Redstone, and in this video we're going to be performing some transformations to linear functions. I've got 4 examples that I'll go through. So with each of them, I'm going to start with the function f of x. It'll be different in each question, but I keep doing it in blue. For this one, I've graphed the function 1/2 x minus 2. And I'm going to transform it into g of x by adding 5 to it. So I take my function f and I add 5. That gives me a new function, 1/3 x plus 3, that I'm going to call g of x. What I've done is added 5 to the output. So if I were to graph it, you see these 3 points, and I'll connect them with a straight line. It's kind of finicky, so bear with me. And yeah, there it is. What we get is a line that's parallel, that is 5 units above it. So by adding a number to the output, we translate our function upwards. If we wanted to translate it down, I would have subtracted a value from the output. But all the y values in the red graph are 5 more than the function in blue. For the next function, I'm going to start with f of x at 2x minus 4. So my y-intercept is -4, my slope is 2. Here what I'm going to do is replace my x with x plus 3. So essentially I'm adding 3 to each input. And what I'm going to do is substitute that x plus 3 everywhere I see an x. So g of x is going to be 2 times x plus 3, subtract 4. I'm going to distribute and collect my like terms, and I'm going to end up with 2x plus 2. And that's my new function, g of x. So again, what I've done here is added 3 to the value of each input. When I graph it, I get this line in red. You can see it is parallel, but I've shifted it left. In fact, I've shifted it left 3 units. And that's evident by what g of x was defined as, x plus 3. That caused it to shift left 3 units. If I wanted to shift it right, I would have subtracted a value from the input. So f of x minus, say, 2. That would cause it to go right 2 units. Next example. I'm going to start with my function in blue. F of x is equal to 1/2 x subtract 3. So it's got a y-intercept of -3 with a slope of 1/2. And I'm going to do 2 different questions here. I'm going to start with saying that g of x is the opposite of f of x. That's the same as taking our function and multiplying by -1. That would give us -1/2 x plus 3. So we get a y-intercept of 3, a slope of -1/2. Connect those up and extend it. There we go. What we have is a mathematical reflection. We have reflected it over the x-axis. Now, if you want to figure out what the transformation that would make it flip over the y-axis, I'll leave that to you. You should also notice that the x-intercept remained unchanged by multiplying by -1. So now to give myself some room, I'm going to delete what I just did, and I'm going to now graph h of x. H of x is going to be 2 times the value of f of x. So what we're doing is multiplying the output by 2. To do that, I take my function f and I multiply it by 2. That gets me x minus 6. So you can see the y-intercept is changed and my slope is changed. So my y-intercept is -6, my slope is 1. That right? Yeah, that'll work. Okay. So here what we have is called a vertical stretch. The y values are increasing, or the output is increasing twice the rate. So take a look at the original distance on that blue graph. It was 0 to 3. Now it's 0 to 6. So the distance away from the x-axis is now twice as much. There it was 2. Now the distance away is 4. Again, we call that a vertical stretch. It is twice the distance from the x-axis. The y-intercept is changed. The x-intercept stayed the same. So this is the last one we're going to do. I've got a function in blue, 1/2 x minus 1, and now I'm going to multiply the input by 2. So I'm not multiplying the output, I'm multiplying the input. Everywhere you see an x, you're going to replace it with a 2x. So g of x will equal 1/2 times 2x subtract 1. Or g of x is equal to x minus 1. So our y-intercept is -1. Our slope is 1. And I will graph that. And I will curse this thing for trying to snap. How do I turn that snap off? You're hearing my innermost thoughts. Oh, there it is. Okay, good. Okay, so when I compare these two graphs, I see the x-intercept has now changed. It's half of what it was. And the y-intercept stayed the same. So this time what I want to do is look at the distance to the y-axis. So I'm going to compare a few points. Here, the distance from the y-axis to our original function was 4, and after the transformation, it was 2. Initially, it was 8, and now it's 4. So this transformation of multiplying by 2 made it twice as close to the y-axis. That's it for this video. Hopefully it helped. As I tell my kids all the time, when in doubt, graph it out. Bye for now.